Good morning. Now we'll begin vectors at higher level. To begin with, within the higher vectors course, much of the first few assignments is revision of National 5 coursework. So you'll be glad to know you should have seen most of this before. It's quite a few lessons before we get to the new higher coursework for vectors. So to begin with, a very quick reminder of what a vector is compared to a scalar. A scalar is size only. We use the word magnitude for that to describe size. Glasgow is 11 miles from Airdrie. That's just a size. We have only just given you a distance there. But if I was to say that Glasgow is 11 miles from Airdrie on a bearing of 270, I have now just described the size along with the direction. So quantities with both size, magnitude, and direction are called vectors. We use components to display a vector. Vector is named using either the letters at the end of a directed line segment. Now notice within this line segment we have got a line that starts at A and finishes at B. We've got a little arrow in the middle of that line to show the direction. So we can see from the size of the line what the size is, and we can see from the arrow what the direction is. We can name this using the letters AB with the arrow above it to show that it goes from A to B. Starts at A and finishes at B. We can also use the letter U. If you see it in a textbook or on a printed document, you will see it normally in bold. Because we can't write in bold, we use an underscore of a line. Underline just to show that it is the vector U. So we can represent a vector by its components and we write them as a column in this way. This would be a vector in 2 dimensions. The 3 along the x-axis and the 2 along the y-axis. So it's along with the first number and up or down with the second number. Very similar to a coordinate. And there are similarities between vectors and coordinates. I'll describe the differences as we go along as well. So a vector AB starting at A finishing at B could also be named U, and to be able to show what this vector looks like, it has the components 3, 2. So on a little scaled diagram here, we have that vector. Now, the starting point from a vector is one of the big differences with a vector and with a coordinate. A coordinate starts at the origin, and a coordinate is a dot. A vector is a line. A vector has a starting point and has a finishing point, and it can start anywhere you choose. That's the big thing about a vector. It can start from anywhere. So we started it where you can see the beginning dot. We could have started it anywhere in that diagram. But from that beginning dot, we have to go along 3 horizontally, and we go up 2, and then we put a finishing dot, and then we join that up with a line from start to finish. To show that it started at A and finished at B, we have an arrow in the middle that points in the direction of where it started from to where it ends. We've also got the letter U to show that it could also be called U, vector U. So here we have vector CD, or we could call it vector V. So we'll pick a place to start, and from that place to start, we'll go horizontally along 3, and we will go down 4. So there we decided to start there, and we've gone along 3 and down 4. So we can see that we've started here, gone along 3 and down 4. And that's us from start to finish. We label it from C to D to just make sure we know where we started, where we finished, and we've also got vector V as the other way of labeling that vector. We've got the arrow on the vector to show that it starts at C and finishes at D, and we call these column vectors. The size of a vector, the length of a vector, can be worked out just as we would a diagonal line in Pythagoras, using Pythagoras' theorem. So if we have the vector PQ, remember that means that it goes horizontally along the first number and vertically along the second number. So those are like the vertical and horizontal lines in a right angled triangle. So from Pythagoras, if we were trying to find the vector PQ, the magnitude PQ, and the magnitude for PQ is shown with 2 vertical lines at the side of the vector PQ. That's how we show the magnitude that we're looking for the magnitude. So in Pythagoras, we square the horizontal and the vertical. We square the 2 numbers, we add them together, and then we square root them. So we just do that all in the one go. So we square them, we add them, and then we square root them. Very simple. If it is a three-dimensional vector, and you've seen three-dimensional vectors in National 5, where we would introduce a z-axis, a point in space would be described with a three-dimensional vector, not just on a flat surface. So we square the three of the numbers, and we add them, and we square root them at the end, just exactly the same. So if we've got a little example here, the magnitude, so it doesn't have to have the word magnitude in the question, as you will know from National 5. We just have to have these little vertical bars beside the vector u, and that is asking you to find the magnitude of u. So we very simply square the 5 plus square the negative 12, and don't forget that's a negative number. Squared is a positive, a negative times a negative is a positive. So 5 squared is 25. 12, negative 12 squared is positive 144. That gives us 169, square root 169, and we have 13. Now it is a size. We don't have centimetres, millimetres. We don't know what the length of the units are, so we just put the word units in when we don't know what to call them. Okay, and here's an example for 3 dimensions. We square the 3 numbers, and we add them together. Don't forget the negative 2 squared is a plus. We have 16 plus 36 and a plus 4 at the end. We add all of that together, and that's root 56. Now we can change it to a decimal if we have a calculator, or we can keep it as a simplified surd if we don't. Vectors with the same size and direction are equal. So for example, here we have the vector u. Okay, we can see from the start to the finishing point, we've gone along 1 and up 2. We've got another vector along there, which is v, but you can see from that we've actually also gone along 1 and up 2 to describe v as well. Now they're not drawn in the same space, they're not drawn in exactly the same position, and that's the whole point about a vector. They do not have to have the same starting point. They can start anywhere, so long as from where you start, you can describe it in the same way. And there we have a vector w that's also going along 1 and up 2. So these are all equal to the vector 1, 2. So equal vectors have equal components. Not really a surprise. Okay, we could use that then to do things like this. And again, this is something you'll have seen at National 5. So we have got a vector A, which we have described as 2x for the first component, and the second component is y plus 3, and the vector B is 6 and 9. We're asked to find what x and y is if vector A is equal to vector B. So very simply, you match the components. The 2 top components are equal and the 2 bottom components are equal. So 2x is equal to 6. So x is equal to 3. That's simple. Do the same with the 2 lower components. Y plus 3 must be equal to 9. So y is equal to 6. And that's very, very simply how you would do that. Now, the next thing we have to do are some questions from the Heinemann Higher Maths book, 13A, questions 2 to 5, and 13B, questions 1 to 4. Message your teachers if you're having any problems with any of the questions, and good luck. Bye.